That's something, I mean, thank you.
So I just turned it on.
Thank you. I'll tell you about some arithmetic aspects of these problems.
Yeah.
There's Can you hear okay now?
Yeah.
Is that good? Okay, good.
So what I tell people about the boards is there's two moving boards.
Oh, okay.
And it's best to restrict to those because
Yeah,
the
yeah.
bottom can't
Yeah,
be
yeah.
seen in the back. So if you write on the bottom, you
I'll
can
do
see
that.
the
Yeah,
bottom
yeah.
moving
Right.
boards. And we're asking the questions that are asked.
Got it.
So the whole room can hear and also so the recording does.
Got it. Okie doke. Yes, I am.
All right, so we're pleased to have Nima Arkanai here to tell us about effective field theories.
All right. Well, it's wonderful to be back at TASI. I think this is the third time that I've lectured here. Every time I come, I make the following obligatory comment that it's a real honor to lecture at TASI, especially because I was rejected by TASI as a student. So, and somehow I find myself saying this every time and laughing about it, but I'm crying inside. Okay? I still have a lot of energy about it, apparently. I don't know why.
You didn't miss very much at that one.
I sure as freaking hell did. It was TASI 95 for the string duality revolution. Yeah, I missed a lot. Anyway, assholes. I'm sorry. No, I'm still sad about it. Anyway, forget it. The next time I'm invited, if I am, I'll promise not to even talk about it. It's ridiculous. I'm a grown adult. I should be past these things. Anyway. More seriously, it's really a real delight. I was thrilled when Nati asked me to lecture about effective field theory. Of course, effective field theory is one of the most profound sort of quiet revolutions in our understanding of fundamental physics that took place largely in the hands of people like Ken Wilson and Steve Weinberg in the 1970s. And there have been many TASI lectures devoted to effective field theory before. Something that probably you guys don't appreciate. Certainly when I was a student, effective field theory was already very well appreciated by all the experts in the subject, but had not quite percolated into the textbooks yet. So the textbooks were still filled with all sorts of crappy things about renormalizability and complicated arguments so you really had to sort of learn the right way of thinking about things from people who who knew what was going on, who had not yet written books. Fortunately, a lot of these things are in books now. I suspect a lot of these things are much more familiar to you guys than they were to my generation. Nonetheless, I will review some of the basics. Let me mention at least two. There have been a number, but let me mention at least two classic sets of Tassi lectures that were very important for me. One was by Joe Polchinski in the early 90s. Actually, they're both from the early 90s. One was by Joe Polchinski, and the lecture today will be very similar to the first lecture. I have a few more details, but largely similar to the first lecture in that just reviewed the Wilsonian picture for effective field theory. And there's the other lecture series was by Howard Georgi on heavy quark effective theory. Both of these lectures started just talking about the basic effective field theory paradigm in normal sort of relativistic quantum field theory, and then they spent their other lectures talking about cousins of these ideas elsewhere. So Polchinski talked about effective field theory for small fluctuations around Fermi surfaces. And Georgi talked about effective field theory for very heavy particles, like heavy quark effective theory. And by now, there's a whole industry. If those of you who don't know right now will know by the end of the lecture that every single time in any calculation in any part of the physics you see a logarithm, you should go ding, 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 and there's some effective field theory at work, and you have to go find it. Okay, so that's why everywhere there's a log, anywhere, and there's a lot of logs. There are different kinds of effective theories. Soft collinear effective theory. There's effective field theories for, for dealing with the generation of gravitational waves and so on and so forth. Okay, so there are many different kinds of effective field theory. So I'm not going to follow that. I'm not going to copy that strategy. I will, as the previous lecture is, begin by reviewing some of the basic facts about effective field theory. But I'll talk about other things, sort of staying within the world of things that have both relativity and quantum mechanics, and take a different tack that really talks about things that have been highlighted in our understanding in the last 10 or 15 years. Many of these things are really ancient, but they weren't, at the tip of people's tongues until they came back up again around 10 or 15 years ago. That has to do with the following sort of basic fact. If you know anything about effective field theory, and we'll review it, you know that it's all about disentangling the physics of very long distances from very short distances, right? So that we're supposed to be able to talk about physics of very long distances without knowing the theory of everything at very short distances, and all the details of whatever is going on at very, very short distances or very high energies are captured in a finite number of dimensionless, marginal, or relevant couplings that describe the physics at very long distances. And the effect of very massive states, very high energy physics, is encoded in tiny corrections as sort of higher dimension operators in the effective field theory at long distances. Okay, so we'll review that in more detail, but that's the intuitive picture. And I just want to point out that entire picture has the word short distance and long distance in it, as if there's a sort of clear separation between these two things. And that's a very Euclidean idea. In fact, the entire idea of Wilsonian effective field theory is deeply Euclidean. So most of our understanding of quantum field theory fundamentally is deeply Euclidean, but certainly the idea of Wilsonian effective field theory is deeply Euclidean. And the world is not Euclidean. Okay? The world is Lorentzian. And in the real world, it's a little bit difficult to disentangle very precisely what you mean by very short distances and very long distances. For example, 2 points can have a very small space-time separation because x minus y squared can be very, very close to 0, and yet be super far apart from each other, simply very close to the light cone. Okay? So there is extra constraints, extra consistency conditions on the structure of effective field theory that follows from consistency with causal Lorentzian physics. So the Lorentzian aspect of effective field theory is non-trivial. And so that's what I'll talk about in the second third of these lectures, are what we're starting to learn more and more systematically about Lorentzian constraints that begin as sort of simple positivity constraints on the coefficients of certain higher dimension operators in effective field theories. And more recently, and this is actually work that has not appeared yet, but it's been talked about a lot, and it's extremely simple to explain. So there's a very large extension of these old positivity ideas into an interesting kind of geometry, a so-called positive geometry that actually constrains the structure of an infinite number of higher dimension operators in effective field theory. So these are things, the Wilsonian picture of the world grew out of condensed matter physics. There, the ultraviolet is some condensed matter system, some ultimately non-relativistic condensed matter system. And it can flow at long distances to all kinds of fascinating, amazing effective field theories that you've been hearing about and you'll doubtless hear more about in these lectures. But there's something further special about relativity. There is something further special about the consistency of Lorentzian causal unitary physics, which is not true of garden variety effective field theory, certainly not true in random condensed matter systems, but is true in the real world. Okay? The real world has relativity in quantum mechanics, and so it has all these other constraints as well. And that's going to naturally lead to the last part. I don't know if we'll get there, but it's natural to talk about it. Another aspect of having a Lorentzian spacetime is that when it's dynamical, you have gravity. And so we have also seen over the last 10 or 15 years that there's interesting conjectural constraints on the structure of effective field theory that are perhaps surprising to the low-energy effective field theorists, but which directly or indirectly, so far mostly indirectly, follow from some arguments about the consistency of quantum gravity. So these are sort of limitations. There are effective field theories that seem totally healthy to the naive effective field theorists, which somehow can't be realized in any consistent theories of quantum gravity. And I'd like to at least give you some idea of what some of those ideas, of what some of those statements are. The weak gravity conjecture is the sort of simplest one of them. In fact, as you'll see, these ideas are closely related to the Lorentzian consistency conditions on effective field theory that we'll talk about earlier. And if we'll get there, which I doubt we will, but if we get there, we'll even talk about a proof of the weak gravity conjecture, at least an asymptotic proof of the weak gravity conjecture along the lines of using some of the positivity ideas that we'll encounter earlier. Okay, so that's the plan. We're in no particular rush, so stop me with any questions you want. I'm not committed to getting through anything in particular. But this is a list of things that we could talk about. Now, there's a last thing here, which I cannot resist mentioning. The entire Wilsonian picture of the world is put under some significant tension by two major experimental discoveries of the last 20 years. We observed a non-vanishing, at least for all intents and purposes, putting aside some disquieting 5 sigma level tension now between late and early measurements of the expansion rate of the universe, which I hope will go away. But we've seen 20 years ago that the universe is accelerating, most likely just with a cosmological constant, a tiny non-zero cosmological constant. And then more recently at the LHC, we've seen the Higgs and nothing else to come along with the Higgs. Now, neither one of these things are a technical inconsistency of effective field theory. They're perfectly compatible with the rules of relativistic quantum field theory. But they're violations of a certain expectation of naturalness. The whole idea of naturalness was born out of this Wilsonian picture of the world. Okay? So while it's not inconsistent, it can't be inconsistent with the idea is so powerful and deep, there's no actual inconsistency with it. There is something disquietingly off about this sort of Wilsonian picture of the world. I debated whether I would talk about this in the main lectures, but some of the ideas involved are sufficiently speculative that I would rather not do that. But if anyone wants to find me after hours and talk for a long time about naturalness, unnaturalness, crazy ideas for what might correlate very high and very high energy and very low energy physics to give totally bizarre new approaches to the cosmological constant and hierarchy problems, if you get me going, you won't be able to shut me up. So. All right, but that's for perhaps later. All right, so that's the plan. Actually, maybe before starting, just so I have some idea, and we'll go over this anyway, but I just want to have an idea how familiar you guys are with these basic concepts. How many of you think you know what Wilsonian effective field theory is? Okay, be honest. Okay, how many of you have seen the Polchinski-Wilson equation? That's fascinating. It's a complementary side of the room. I don't know how both those things could be true at the same time. Okay, very good. That was a very confusing piece of data. All right. Okay. All right. So let's get started. So again, the basic idea of effective field theory is that whatever the ultimate theory of the world, so long as you make some very mild assumptions that at sufficiently large distances you have a finite number of particles, or if you want to talk in the language of fields, you have a finite number of sort of light fields, then the interaction of those light degrees of freedom are governed by a finite number of coupling constants, okay? And that's totally determined just by dimensional analysis. Okay, so the so-called marginal and relevant couplings that have they're either dimensionless. We're largely going to be working in the framework of perturbation theory here. They're either dimensionless or have positive mass dimension. This Wilsonian picture of the world, it explains renormalizability. Okay, so this is one of the terrible things that we had in the old books. In the old books, people would say, why do we concentrate on renormalizable theories? Because in non-renormalizable theories, we can't predict anything because there's infinitely many undetermined constants, right? And that was what people were still saying in the books when I was a grad student, and it nearly led me to quit high-energy physics because I thought these people were on drugs if they really believed this statement, okay? Why would nature give a rat's ass whether we could compute something or not, right? That's a terrible, terrible argument for why nature should be governed by a particular kind of theory, the one where the theorists are happy, they can make predictions. It's stupid, okay? And in fact, I nearly did quit until I ran into Joe Polchinski's paper, literally randomly thumbing through old issues of Nuclear Physics B, which actually, I recommend that you do. Sometimes it's fun. And then, the scales fell my eyes and everything started making sense. Now, in this Wilsonian picture explains renormalizability. It actually says it's an output that no matter what the underlying theory is, there's some approximation where there's a Lagrangian with infinitely many parameters, but all the higher dimension, all the couplings with positive mass dimension are suppressed by some scale. And if you go to low energies relative to that scale, they're in an important sense, in a precise sense, irrelevant. And all we're left with are the dimensionless interactions of the ones with positive mass dimension. It tells us, for example, it has lots of interesting consequences. It tells us in non-renormalizable theories, like quantum gravity. How many of you think that we can't compute any loop diagram in quantum gravity? So here's another, well, I'm giving away the answer, but let's say, it's quantum gravity, so here is some interaction, with ordinary matter and a graviton and a loop of gravitons. Okay, how many people are scared of this diagram? Very good. There's an honest guy there, okay? So a lot of people are scared of this diagram. Isn't quantum gravity supposed to be hard? Isn't this why we need string theory? Blah, 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 right? It's non-renormalizable, et cetera, et cetera. Well, effective field theory tells you what part of this is actually calculable. You can calculate some, in fact, you can calculate almost all the interesting aspects of low energy, long distance physics. Things that you can actually measure and detect at long distances are calculable at long distances, even when the theory is non-renormalizable. Okay? We can understand why that is. And when you think in position space, it's really things that die off like power laws that you can actually measure at long distances that are calculable, even in quantum gravity. So you can talk about, for example, the one-loop correction to to the Newtonian potential. That's a computable thing that you can talk about. The things that are not computable are contact terms that genuinely have to do with very short distance physics. So you have to go there, right? That's one of the basic lessons of Wilsonian effective field theory. The thing to keep in mind as you go off in physics, the slogan is, you need a microscope to see short distances. Okay, you need an accelerator. You need very high energy to see short distances. But everything that you can in principle see, even if it's a tiny effect, everything you can in principle see at very long distances is calculable in the low energy effective theory. Another feature of this picture of the world is that the renormalization group is the central driver of this way of thinking about things. So the Wilsonian picture of the renormalization group is the key to this whole picture. And that's, again, the opposite of what it used to be like. Again, in the books, it probably doesn't matter to you because you haven't seen these bad, terrible old books. But in the usual way of thinking about things, the renormalization group is like some weird trick. Okay? I don't know if any of you have read any of the terrible old books. Please don't. But if you have, it goes something like this. You're sort of, the derivation of the renormalization group violates all the usual laws of theoretical physics that you never get anywhere mindlessly playing around with equations and identities. Okay? And here, instead, you have this stupid scale mu that shows up, and you say nothing depends on mu, and you say some mu dd mu, and then tuck, all of a sudden, you get this amazing equation that comes out of it. How did that happen? Where's the magic? You never get anything for free in physics. There has to be magic somewhere. And there is magic there, actually. The magic of the renormalization group, and we'll see it in more detail. The magic was something that in the old books was put in the very last chapter that no one read, in the proof of renormalizability. The fact that field theories with dimensionless couplings are renormalizable is actually a non-trivial fact. And it had a non-trivial proof in the old literature, non-trivial, complicated graphical proof that nobody read. It was just put on the very back of the book, goes initials BPHZ, forest, trees, skeletons. I'll say a little bit about it towards the middle of this lecture. But anyway, that's in fact where all the action is. That's where something non-trivial happened, but no one looks there. You just take the result for granted. If you take that very non-trivial result for granted, then indeed the renormalization group just is a piece of cake. But in the Wilsonian picture, it's the other way. It's conceptually ordered correctly, and the renormalization group is the star of the show. And so we'll talk about it in that language. So the RG will come first, and everything else will follow. All right, so let's begin. So I'm going to talk about everything in the language just for toy scalar theories. At some point toward the end of the lecture, I'll tell you what interesting things happen when you have spin. So effective field theory is one of two things we learned, which is, again, one of these sort of quiet revolutions of the last 40 years. The largest statement is that whatever the underlying theory of the world, so long as at long distances you assume there's a finite number of particle species, then what that theory at long distances must consist of fields or particles of spin 0, 1/2, 1, 3/2, and 2. That's the only menu you're allowed to have. If there's spin 2, there can only be one of them, and it's the graviton. It has universal strength, and it's GR at low energies. And you can just derive that from the consistency of special relativity and quantum mechanics. You can have spin 3/2, but you can have at most 8 of them. And if it exists, the world has to be supersymmetric. You can have spin 1, but it has to have the structure of Yang-Mills theory, and so on. Okay? So the gross features of the world that we see around us are almost completely determined by the basic consistency of special relativity and quantum mechanics. And those particles that you can have, the dominant interactions they have at low energies, are the ones that we associate with cubic couplings, and exceptionally in the case of scalars, some quartic couplings as well. It's the second part, the fact that the interactions are these very limited ones, which is the consequence of the basic philosophy of effective field theory. And this has very little to do with spin. So we'll talk about all of this in the context of just simple scalar theories. There is something new that happens when you have spin. And the new thing has to do with the discontinuous difference between the number of degrees of freedom of massless and massive particles. Okay? Massive particles with spin, for example, massive spin 1 particles, have 3 degrees of freedom. Massless spin 1 particles have 2. So the effective mass is not just this little tiny kinematical correction, which is what you would have naively thought. You can't be a little bit massive, just like you can't be a little bit pregnant, a fact all too familiar to many undergraduates. Okay, so so there is something discontinuously different between being massless and massive, and that is the source of much of the other drama of the 20th century. In the standard language using local quantum fields, we have to accommodate this discontinuous difference between massless and massive degrees of freedom by introducing gauge redundancies. Gauge redundancies for massless spin 1 particles, general covariance as a redundancy for massless spin 2 particles, and so on. So this is the second part of the story that crucially has to do with spin. So the consistency of massless particles with spin is what puts a big constraint on the menu of possibilities and limits it to things up to spin 2. Then, once you have that, the kind of interactions that they enjoy, the fact that we don't have to deal with fundamental 12 particle interactions, but we can build everything up out of the very, very simplest possible interactions we have as a consequence of the general effective field theory paradigm. Okay? I will not talk about the business that has to do with spin. I believe Mark Spradlin in his lectures on scattering amplitudes, and at least in his first lecture, will give you some idea of how incredible these constraints are from relativity and quantum mechanics and why that forces this structure on you. But together, these two ideas that massless particles with spin is the mass is a non-trivial perturbation. Dealing with massless particles at first puts this tremendous constraint, so you can't talk about particles with spin bigger than 2, and you get exactly the kind of structure we see in the world around us on the one hand, coupled with the effective field theory paradigm that tells you what kind of interactions to enjoy on the other hand, essentially from pure thought, given the principles of relativity and quantum mechanics, tell us that the long-distance world has to look something like what we've seen. Okay, and I think that's one of the tremendous triumphs of fundamental physics in the 20th century, that starting from these two giant principles, we get such a good zeroth order understanding of the gross features of the world around us. It's like an absolutely astonishing thing. So, but for the second part of that, you'll get a flavor of it from Mark's lectures. We're going to ignore spin and just talk about a model scalar theory. All right, so I'm not going to care about factors of 2 and so on. That should be obvious. But let's say we have a simple scalar theory. Let me call these interactions H4. There's all kinds of things that I could write down here. Okay, so we're not restricting ourselves to renormalizable couplings. Let's just write down the sort of most general Lagrangian that we can imagine for this massless scalar. Now, let's begin with the standard bit of dimensional analysis. So you know that just by looking at the free kinetic term, we conclude that in d spatial dimensions, the scalar field has mass dimension d minus 2 over 2. And using that, we can see immediately, since the whole Lagrangian has to have mass dimension d, we can see immediately that when we go to sufficiently high terms in this expansion, these coupling constants have to have units of inverse mass. They have to be suppressed by some heavy mass scale. Okay. So for instance, if I look at an amplitude for 2 to 2 scattering, this has a piece from H4, but also has a piece from H8, but H8 has 4 extra momenta in it. So I'm going to be very schematic with momenta and so on here. Let me just say something like p to the 4th H8. Okay? And so you see that H8, if I now work with dimensionless couplings, I would put H4 as some lambda 4, which is dimensionless. H8 is, let's say, lambda 8 over some cutoff scale to the 4th. Then I see that this is lambda 4 in terms of dimensionless couplings plus lambda 8 p to the 4th over lambda to the 4th. And so in the most obvious sense, you see that the effect of this higher dimension operator, called a higher dimension operator simply because it has a negative mass dimension, at low energies, its effect is suppressed relative to this one, which is dimensionless. Okay, it's totally obvious that it's just dimensional analysis. When the couplings have units, there's no sense in which they're big or small. They're big or small relative to some energy scale in the problem, and when the energies are small compared to that scale, they're tiny, and when they become comparable to the scale, something new happens, because after all, we also learned from this formula that when the momenta become comparable to lambda, this expression can't really make sense anymore, right? When the momenta become comparable to lambda, this amplitude is becoming of order 1. The amplitudes can't get bigger than 1, because when you mod square them and add them all up, all the probabilities have got to add up to 1. So we see that an expression like this might make sense at very low energies. At very low energies, when p is much smaller than lambda, this term is irrelevant. It's a tiny correction. If you did a very, very accurate measurement, you might detect it. And so you could tell that it's there. But in any case, as you go to higher and higher energies, at some point it does become important. At the point it becomes important, we can't really trust this entire expansion anymore. All the higher and higher derivative terms or the higher and higher dimension operators start becoming important. And so we have to go over into a new description of the physics. Yes, there was a question back there.
Why do we not care about odd powers?
Oh, I'm just for simplicity. I said there's some. Oh, I'm sorry. He said, why don't I care about odd powers? I'm just so, because I'm lazy. I'm imagining there's a phi to negative phi symmetry. Okay, but later I won't. Sometimes I won't. So then just ask me. Okay. Now, let me make a little aside here, because I find that even this is an extremely basic point, which I think should be slightly better appreciated than it is. So this is an aside. So what is the meaning of this dimensional analysis? So when we say that phi has, I mean, I don't know about you. Well, certainly when I first saw this kind of seems a little lame, right? So you do this thing, you do this engineering dimension, it has these units. So what? So what we seem to what's the invariant significance of the fact that we have that we say that phi has that engineering dimension? Well, here's one clear aspect of it. Let's say I look at, just even in the free theory, if I look at a 2-point function for phi, then this tells me without doing any work that it goes roughly like 1 over, well, if it's massless, it goes like 1 over x minus y to the d minus 2. Okay, so that's something that I learned that has some content. So this engineering, this dimensional analysis is making a prediction for what the 2-point function is, right? But I want to say this even slightly more. I mean, this is an extremely elementary point, but I want to say it, stress where this is coming from even slightly more physically. To do this, I want you to imagine for a second that we thought of putting the field theory on a lattice somehow. And so on each site, we have some sort of phi sub I. All right? And so the Lagrangian would be some phi sub I squared dot squared. And then it has some gradient terms, right? From minus grad phi squared. So this is some phi I minus phi I plus its neighbors divided by some lattice spacing squared plus, and so on, right? The sum over neighbors. Now, just for a second, let's imagine shutting off these spatial gradient terms, right? If we shut off the spatial gradient terms, then what do I have? I just have a separate quantum mechanics problem, a separate just free particle, free quantum mechanical particle on every single site, okay? And now just think for a second, in the ground, so what does the ground state wave function look like for a particle in a box? Let's say I put it in a humongous box. What does the ground state wave function look like? It's completely delocalized in the whole box. Okay? So if I ask what is the expectation value of in a big box, right? If I ask what is the expectation value of x or x squared in a big box, well, the expectation value of x squared gets bigger and bigger as the box gets bigger and bigger. Right? So in quantum mechanics, the wave function is totally delocalized. And yet, when we do quantum field theory, we talk all the time about things like the expectation value of phi. So what the heck is going on, right? In quantum mechanics, the expectation value of x is not a particularly well-defined, decent quantity, right? In a big box, the expectation value of x squared, the fluctuation gets larger and larger because it's totally delocalized. Whereas in field theory, we happily talk all the time about the expectation value of phi. And the difference is exactly these spatial gradient terms. Okay? If I didn't have the spatial gradient terms, field theory would just be a ton of decoupled quantum mechanics. But the spatial gradients suppress the fluctuations, right? If I have a fluctuation on this site, it's surrounded by a lot of other sites, and those gradient terms become important. And clearly, as you go to larger and larger dimensions, every site is surrounded by more and more things on the outside, and the spatial gradients become more and more important. Okay? So let's talk about something. Let's talk about what the ground state wave function looks like for this free scalar field. Okay? You know what the ground state wave function looks like for a harmonic oscillator. Psi of x equals e to the minus omega x squared. Right? Where omega is the frequency. And so what does the ground state wave function look like in field theory? You can think about field theory as just for each k mode, for each momentum mode, you have a separate harmonic oscillator. So the wave function, you could think of a wave functional for some phi of x. So you give me some phi of x. I ask, what does the vacuum wave function look like when evaluated in that phi of x basis? Well, it's very simple to see what this is. It's just the product over all the k modes of e to the minus omega k. So let's say it's a massless particle. So omega k is the magnitude of k times phi k mod squared. I'm just being a little loose here, right? So this is e to the negative, the integral, if I'm in little d spatial dimensions, k phi k mod squared. Okay, d is the number of spatial dimensions here. Okay, good. So that's what the, it's Gaussian. That's what the Gaussian vacuum wave function looks like. But let's just be a little more intuitive about it. So let's say I give you a fluctuation. Let's say I ask, what is the probability, or what's the amplitude that in the vacuum I find in a bubble of radius r, phi to be some value phi naught inside, and phi is like 0 out here. So I want to know what is the vacuum wave function evaluated on this sucker. Is it clear what the question I'm asking is? Right? So what's the chance, what's the probability that there's a fluctuation in the vacuum that gives me phi naught in a bubble of size r? And this is the other thing that dimensional analysis just gives you the answer for. You don't have to think. It's Gaussian, so it's e to the minus phi naught squared, and then the rest is made up by units. So r to the power of the space-time dimensions minus 2. Okay? So these are all just ways of saying the same thing. It's a Gaussian problem. In Gaussian, everything is determined by the two-point function. We could talk about the two-point function in position space, and so dimensional analysis just tells you that as you go to higher and higher spatial dimensions, the two-point function drops like a rock more and more. It also tells you that if you ask for the amplitude for a bubble to with the size phi naught inside a radius r is e to the minus phi naught squared times r to the appropriate power determined by dimensional analysis. These are all equivalent sort of trivial statements about the Gaussian free wave function. But it has some important consequences for the structure of field theory. So when d equals 1, so that we're dealing with quantum mechanics, then the fluctuation, that's what we expect. The fluctuation grows as you go to larger and larger r. And that's just what we talked about. That's just the fact that the free particle is totally delocalized in quantum mechanics. So the fluctuation grows. And d equals 2. 2 is always a critical case in quantum field theory, as you all know. So this r to the d minus 2 actually tells us that the size of the rough size of the fluctuation of phi naught actually grows like log r. Okay? So it's actually something that grows logarithmically. Okay, and that's another sort of simple deep fact. That's why there's no Goldstone bosons in 2 dimensions, for example. Okay, the reason we can't have Goldstone bosons in 2 dimensions is that while in higher dimensions it makes sense to say you're at the bottom of the Mexican hat somewhere, and the massless scalar field, the Goldstone boson, doesn't have fluctuations on very large distances. You can't say that in 2 dimensions because that massless degree of freedom that you think is there is logarithmically fluctuating. But in d bigger than 2, the fluctuations die at large r. And so, for example, we can talk about the expectation value of a scalar field. That's a meaningful concept because the size of the fluctuation as the bubble gets larger and larger, it gets smaller and smaller. I want to give you a little fun example for you to work through. Just again, since this dimensional analysis is so important to us, I just wanted you to get some idea, a little bit more nuts and bolts idea of what it means. But let me just give you a little immediate application by looking at the following pictures. Let's say I hand you a potential that looks like negative m squared phi squared. Boom. Right? How many people think this is unstable? And that it's disastrous. If the world looked like this, it's disastrous. You know, we wouldn't find ourselves near the top. How many people think that's okay? Come on, guys. Not a trick. So far, not a trick question, right? Okay, I think we all agree this is terrible, right? If you're at the top here. And by the way, if you're at the top, how long are you going to survive at the top? Huh? No. Quantum mechanically. Quantum mechanically, if you're at the top, how long will you survive at the top? Any guesses? Just dimensional analysis. 1 over m, right? So the lifetime to sit at the top is of order, well, we could say it many ways, but all the scales are like 1 over m. Okay, so the t death is of order 1 over m. Okay, let's do another example. Let's say your potential is mu phi cubed. Okay? Okay. Now that potential looks like this. What about this guy? Not quite as bad, right? What about in this case? This also doesn't look too happy, right? So what do you think happens here? Is it stable or unstable? Clearly unstable. And we need to have a few more brave people if we're going to have fun in these lectures, okay? I promise not to crucify anyone. What's the instability time? 1 over mu, right? T def is 1 over mu. Okay, let's keep going. So let's say that we have let's say we have v of phi is negative lambda phi to the 4. Okay? What about this? Are we safe or unsafe? First of all, just at 0th order.
Unsafe.
Unsafe? Okay, but what is the lifetime? Ruh-roh. What is the lifetime? Huh? Log lambda? Nyet. What are the units of lambda, my friends? Dimensionless. Okay. So what's going on?
You need a scale to define lambda.
Sorry?
You need to define lambda to give the scale.
That's fine, but do whatever you want. What do you think? I mean, just let's say lambda at whatever scale you want is negative 0.001.
Well, then you try to dimension quantities. You define it with the scale.
Good. But I'm telling you, tell me whatever scale you want. Let's say at 10 TeV, lambda is negative 0.001. Are we dead or alive? By the way, this is not an academic question. This happens in the standard model. Those of you who have heard that in the standard model there's an issue with the stability of the Higgs vacuum, this is just what's going on. As you run the quartic coupling of the standard model to high energies, we'll understand those words better by the end of this lecture, but as you run to very high energies, the quartic coupling is negative. This is exactly what's going on, and we're not dead. Okay, there's a good reason we're not dead. Right? Huh? So we're not dead anyway. Yeah. All right. So let me actually point out another feature. Let me point out another feature, which is, let's say you did perturbation theory in this theory. Okay, you're computing perturbation theory. Do you see that you're dead? Do you see anything about the fact that there's vacuum instability or so on to any order in perturbation theory? You draw diagrams, you don't see anything. Okay? In fact, I encourage you to think. I don't want to spend too long on this example. This is really meant to illustrate the usefulness of thinking about understanding the origin of this dimensional analysis. But I encourage you to do this exercise and just try to convince yourself that, in fact, in no order in perturbation theory do you see any instability in lambda. Okay? And perturbation theory is not stupid. Perturbation theory never lies to you. And if there's something that does not occur in perturbation theory, that means that if it's there, it's non-perturbative. And in fact, there is an instability here, but the lifetime is e to the minus 1 over lambda. You don't see it any order in perturbation theory. But let's see if we can understand that. We can understand it very simply. You see, how do any of these instabilities work? Well, let's do literally this example. You might say, oh, I know what's going on. I'm just sliding off the top. Look how terrible it is. I'm just going to slide off the top, right? But, you see, when I'm sitting at the top, in order to slide down, everywhere, and to literally think of it as this particle mechanics picture, everywhere in space at the same time, phi has got to fluctuate coherently in one direction. Okay, and the probability of that happening is 0. So actually, let's get an idea of what you actually need. What do you actually need? You need to make a bubble here, and let's say that inside the bubble you have phi naught. How big does R have to be in order for you to hit death? Well, gain an amount of energy, which is lambda phi naught to the 4th times R cubed. That's the gain. But there's a loss. The loss is from the gradient energy here, right? The gradient energy is of order, well, just phi naught squared over R squared times R cubed again. Okay? So in order for this, in other words, if I make the bubble too small, then the gradient cost is too big, right? And so I will make the bubble and it collapse under its own pressure, right? In order to make this bubble that's going to destroy the universe, it has to be big enough to at 0th order have 0 energy, right? And to have a balance between the potential and the kinetic energy. So if I solve this, I get a formula for R. In fact, let me do it a little more directly. We see that phi naught squared R squared has got to be of order 1 over lambda. That's a beautiful formula, you see? Because it tells you that R has got to be bigger than 1 over phi naught by this amount, 1 over root lambda. Now let's go back to this exercise was in 4 dimensions. Now let's go back in 4 dimensions and ask, what is the amplitude to find? What is the amplitude to find? What is the amplitude to find in this bubble R phi naught such that, so remember, this is e to the minus phi naught squared R squared, and this is e to the minus 1 over lambda. So the amplitude to create the bubble that will kill you is actually exponentially small in 1 over lambda, is non-perturbatively small. Okay? So we've already learned something interesting. Now, what's going on in our previous examples? In our previous examples, it's exactly the same logic. It's just that R, for example, in the mu phi cubed example, R needs to be of order 1 over mu. Okay? And so in this case, the amplitude could not be made bigger and bigger by making R bigger and bigger. Lambda was dimensionless, and so this answer is actually scale invariant. at leading order, at this order. Later, we'll talk about the running of this coupling and so on if we were to do this example more carefully. But at 0th order, this is dimensionless. All bubbles of all sizes contribute equally. However, what would we get for the phi cubed example? We get e to the minus 1 over mu r. All right? And so there, it's not scale invariant. And if you allow r to get bigger and bigger such that r mu is of order 1, then poof, right? It's totally unsuppressed. Now that's illustrating a very important point. What is a dimensionless size of that cubic interaction? The relevant dimensionless size of the cubic interaction, it's dimension full, right? So its actual dimensionless strength is actually mu times r. If you allow yourself to go to lower and lower energies, that's a coupling of positive mass dimension, so it becomes more and more important as you go to longer and longer distances. So this is actually an example where you allow that cubic coupling to become non-perturbatively large as r gets big. Okay? When r becomes of order 1 over mu, the dimensionless size of the interaction is 1, and so poof, you are unstable. Right? By the way, this makes an interesting prediction. What if you took this mu phi cube theory and you put it in a box? Take that mu phi cube theory and put it in a box, and make the size of the box much smaller than 1 over mu. Then, once again, the lifetime would be exponentially long. See, perturbation theory never lies. Even in the phi cube theory, perturbation theory doesn't lie. You don't see the instability to any order in perturbation theory. It's just that in the infinite space, the phi cube coupling becomes big. Right? That's a dimension-full coupling, and it becomes huge. It becomes of order 1. And so the non-perturbative effect associated, the non-perturbative effect that we're talking about happens on a timescale of order 1 over mu. Okay? So it's pretty cool. If you take this phi cube theory in a tiny box, it's actually exponentially long-lived as well, despite the appearances. So this is just an example. It's jumping in to the middle of all the discussion, but I thought before we did back to slightly more formal things, I just gave you maybe a slightly less familiar example than the cookie cutter ones that you've seen in your courses for how this dimensional analysis stuff actually matters. Okay? And in the real world, the quartic coupling of the Higgs runs negative. If you just have the standard model and nothing else, it runs negative at a scale of around 10 to the 10 GeV. Fortuitously, it never gets much smaller than negative 0.01 or so. Okay, and that's why the vacuum is exponentially long-lived, even if much, much more long-lived than the age of the universe, despite the fact that at that scale, really potential really looks like that. Okay, but for these for the reasons that I talked about, can be exponentially long-lived. So 2 morals from this little exercise. 1, the importance of the dimensional analysis. You see that the dimensional analysis is really controlling the quantum fluctuations in the vacuum. The spatial gradients are the novelty in quantum field theory over quantum mechanics. The spatial gradients in sufficiently many dimensions suppress fluctuations of scalars, suppress fluctuations of field at long distances. That's the first lesson. The second lesson from this little example is perturbation theory never lies to you. Okay, it never ever lies, and you should figure out if there's some effect that doesn't occur in perturbation theory. Maybe it occurs non-perturbatively, but what's going on in these examples is exactly these couplings that have positive mass dimension. You allow them to grow and become non-perturbatively large at sufficiently large distances. All right, so back to the regularly scheduled effective field theory lecture. Although, any questions about that? Okay. So, so let's go back to our example, and immediately we can see something. I mean, we just saw it. So let's say again, in that example, we just saw already that if I took the 4-point, I would get lambda 4 plus lambda 8 over cut off to the 4th, p to the 4th, plus dot, 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 right? Or if I looked at some 6-point, so here's another interesting example. If I look at 6-point, what would I get for this 6-point interaction? Well, one piece would just be H6, But there's another way I could get this 6-point amplitude. That's one diagram. The other one is to take a 4-point exchanging a massless particle on the inside. So that would give me h4 squared divided by p squared. Okay, so here again, the total amplitude for this 6-point process would be h6 plus h4 squared over p squared. And once again, you see now there's a p squared downstairs. So as you go to lower and lower energies, this process is dominated by the dimensionless couplings that you have already instead of the higher dimension operators that might be sitting there. Okay, so it's over and over again the same very basic point. Just by dimensional analysis, it looks like we should just be able to, at 0th order, just throw out all of the irrelevant operators, right? All the higher dimension operators, they don't matter. Just ignore them at very long distances. After all, and there's many analogies for this. It's so simple, we don't need to make a lot of analogies. But we're very familiar with something similar when you talk about some complicated distribution of charge. Right? When you talk about some complicated distribution of charge, here are some very complicated distribution of charge. But you're very familiar with the fact that from super duper far away, what do you first notice about this? You don't see any of this structure. So if this characteristic scale is A, if you go to distances r that are much, much larger than A, at 0th order, it's just going to look like a point charge. So the first thing that you notice about it is that the electric field, let's say, goes like some total Q over r squared. And maybe if you do a much more accurate measurement, you might see that it has a correction that goes like some d over r cubed. And it has further corrections. And you would interpret that d over r cubed as saying, aha, this is not just a point. It has some distribution of charge, so it's a little oblate. Okay, so the total Q goes there. The fact that it's oblate goes there. A quadrupole moment, and so on. So those are ways that from very far away, you encode some information about what this distribution of charge actually looks like. But the first thing that matters is the total charge. Only if the total charge happens to vanish, then the next thing that matters is the dipole moment. It goes like 1 over r cubed. So you organize your thinking about what this distribution of charge looks like from very long distances just by this multipole expansion. And all the higher order terms, and in fact the higher order terms explicitly, like what is the size of the dipole moment? D roughly goes like A times Q, right? If this is a spread out distribution, so you explicitly see that this correction d over r cubed, so E goes like Q over r squared, but it has some correction that goes like A over r times Q over r squared plus dot 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 dot, right? So this is explicitly suppressed by powers of the microscopic scale that governs what the distribution actually looks like, divided by the long distances from which you're measuring it. Okay? So we're very used to this idea, very elementary idea in physics, that something that we're looking at from far away, something small that we're looking at from far away, we encode the information about what it looks like that we have access to far away in a systematic expansion that's suppressed with higher and higher powers of ratios of the small scale divided by the long scale from which we're measuring. When we are talking about amplitudes or correlation functions in quantum field theory, we're talking about ratios of the energy scale divided by powers, again, of whatever the ultraviolet scale is associated with the physics that we don't see. Okay, but this is such an obvious and simple idea. Why were people confused about it? Okay, why was there any confusion about these issues at all? And actually, the reason for all the confusions, for the sort of 20, 25 years of confusions about the subject, all has to do, of course, with the ultraviolet divergences in quantum field theory. Okay? See, all of this is pure dimensional analysis, okay? And it seems sort of totally obvious. And yet, you can do some things that, and yet first of all, there's the general naive confusion about ultraviolet divergences when you do concrete calculations. Just to give you a very simple example, this actually turns out not to be one of the deepest or the most important ones for reasons that will become obvious, if it's not already obvious to you, in a bit. But let's just see why I can't just do this most naive thing. See, the most naive thing I'd say here is H6, right? H6 goes like some lambda 6 divided by cutoff squared, let's say. And I just want to say, look, H6 just doesn't matter at low energies. Why don't I just do the calculations by throwing out H6? Clearly, it doesn't matter. We just saw in our examples. I calculate something at tree level, and it doesn't matter. Well, one reason you might be confused is that you can calculate a one-loop diagram. Right? So let's say you calculate that one-loop diagram, which contributes to the 2-to-2 scattering, right? Contributes to the 4-point scattering. Well, what is this? What is this diagram? Here, we don't actually have to do a calculation because it's clear ahead of time what's going to happen. The 4-point the 4-point amplitude, the 4-point coupling is dimensionless. This thing is proportional to H6. So whatever is going on with this loop has got to undo that cutoff squared and give me something dimensionless. That tells you without doing any calculation that you're actually going to encounter a power divergence if you do this integral. And of course we do, right? Here I get a d4k, if I'm in 4 dimensions, divided by k squared. Just from that propagator, and that also goes like the cutoff squared. So this thing is H6. Sorry, this was lambda 6. Lambda 6 over cutoff squared, so this goes like lambda 6. So that appears to say that I can't just throw out. I mean, I have some fixed theory with all these higher dimension operators. I would like to throw out the higher dimension operators, but apparently I can't, because if I do quantum corrections, they're going to come back. Okay, so that's one source of confusion. A deeper issue to confront are not these power divergences that are kind of, in a precise sense, sort of meaningless. We'll come back and talk about this in more detail later. But here they're certainly not meaningless. In the computation, they're sitting there. So we're going to address it right here, right, in this context, and I'll explain how to think about it. But just to say immediately what the deeper issue is, the deeper issue has to do with logarithmic divergences. And so, as I said, the logs are really what the Wilsonian renormalization group and effective field theory are all about. So every time you see a log, you should get excited. But just to have an idea why logs are special, so the logs are the key. And we're going to describe why the logs are the key in the sort of standard way of doing the calculations, where we really imagine we're doing a Euclidean calculation. Later, we'll talk about why the logs are a key from a Lorentzian point of view as well, because there's different physical reasons, of course, related to each other. But the logs are the key because when you get a log divergence, like log cutoff divided by some momentum scale, this is something that gets equal contributions. This arises from an integral that looks like dk over k that goes from p to lambda. And so the crucial thing is it gets equal contributions from all scales. So we call these ultraviolet divergences, old books call them ultraviolet divergences, but that's kind of doing them a disservice, right? This is not dominated in the ultraviolet. This is something that's there every decade in energy, building up, getting equal contributions from all scales, right? So thinking about this carefully is going to be the key to understanding the Wilsonian renormalization group. Again, that's as distinct from this silly thing, where that is completely dominated in the ultraviolet. Okay, so before getting to the heart of the matter and actually seeing technically how it works, let me just tell you what the correct statement is. The correct statement is that even if you do something like this, even if you play with cutoffs, you do calculations like this, it's possible to absorb away all the effects of the irrelevant operators, the higher dimension operators, simply by redefining, simply by setting them to 0 and redefining what you meant by the dimensionless and the relevant operators to begin with. And all the effects of the higher dimension operators, you can get a different, you can make a different choice for the theory. Slightly change what you mean by the theory. At long distances, low energies, it'll look exactly the same. The differences will only be powers of low energy squared divided by the cutoff squared. But you can set all the irrelevant operators to 0 simply at the expense of redefining what you meant by the dimensionless and the irrelevant ones. Okay, so that'll take care of that part. And then this log is something that gets equal contributions from all scales. This is something that's going to require us to start thinking about field theory slightly differently than people were doing in the 50s. People were thinking about field theory and perturbation theory in the 50s, graph by graph. And what Wilson taught us to do is how to think about field theory scale by scale. And you'll see this has real teeth, and we'll see what the non-trivial content of it is. But to deal with the log divergences and to understand them, we're going to think about physics scale by scale. All right, so that's just setting up some of the actors in our little drama here. So now let's, since the real issues have to do with the logs, let's now talk about some very standard computations you've seen in your field theory courses, having to do with these logarithmic divergences and renormalization and so on, but from the Wilsonian perspective. So I'm going to imagine again, let's say I just have, just for this exercise, let's say I just have a phi to the 4 theory. And uncharacteristically, I put the 4 factorial there. Okay. All right. So that's our phi to the 4 theory, and I'm imagining that this theory is regulated in some way by some cutoff lambda. Okay. Now you can do this any way you like. You can regulate by, for example, in this simple theory, we don't have to worry about things like gauge invariance and so on. You could just imagine you put a hard cutoff on the loop integrals. Okay. But really, this is just a guess for what the real high-energy physics is. The real actual world, if you actually have the scale of this interaction, it's embedded some consistent theory of the world. Maybe it's strings in the ultraviolet, or maybe it's UV completed in some other non-abelian gauge theory that's asymptotically free and makes sense at very high energies. There's a million things that it could be at very, very high energies, which is what's actually going on at very high energies. Okay, but the whole point here is that we don't actually have to correctly guess what's going on at very high energies. Any model for what's going on at high energies will do. Any model at all will do, and they'll give us the same answer for physical questions at very low energies. Okay, so that's what we're going to try to understand and prove. But keep that in the back of your mind. There is some physical thing that's actually going on in the ultraviolet in the actual, in the actual real world ultimately. But in any model that you have in mind, there might be something that actually UV completes it to a sensible theory, but it doesn't matter. You make any guess. So put a momentum cutoff. Imagine you add some heavy particles. Imagine you add things with wrong sign kinetic terms, like Pauli-Villard's regulators that go around loops. It doesn't matter. You make any kind of guess you want that just allows you to make calculations and get, calculation you can put on the computer, right? Have in your mind that you're just choosing a model, right? You're making a model for the system, and so it has some cutoff. Lambda. Let me actually just say right here that thinking in terms of this cutoff lambda, sometimes people say, well, this is very hard to do in other theories. If you have gauge theories, it's much better to do dim reg. For example, if I do dim reg, I don't see any cutoff lambdas and so on. I encourage you to do this as a little exercise for you. Show that dim reg is a UV cutoff of the standard sort on loop integrals, where the cutoff is mu e to the 1 over epsilon. Okay? That's a very simple exercise. And here's how you should do it. Remember, if you have any integral that you do in dim reg, you imagine, for example, in 4 dimensions, it's some d4p and it's over some powers of momenta. It doesn't matter. Okay? And what you do is you say, I'm going to say this is, I'm going to put a d4 minus 2 epsilon there. And I put some power of mu. like I put a mu to the 2 epsilon in front of the whole thing, right? So that's what dim reg is. Now, in order to make this thing UV convergent, it's important that epsilon is positive, right? Because I want to make this a lower dimensional integral. But just in your mind for a moment, imagine that epsilon is negative. Then you have slightly more integrations to do. Do those integrals. Imagine epsilon was an integer. Just do those integrals by hand, and what are you going to get? You're going to get some power of the remaining p squared. You're going to get p squared to some power like epsilon, and that's exactly damping the now when you continue epsilon to be negative, that's exactly damping the very high energy piece of the integrand as if the cutoff was mu e to the 1 over epsilon. Okay? So even dim reg can be thought of as a cutoff, and you see log lambda over p becomes log mu over p plus 1 over epsilon. Right? So those are the usual 1 over epsilons that you see in dim reg are actually just the logs, just the big logs that we talk about with ordinary physical cutoffs. So there's nothing sacrosanct about dim reg, nothing special about any of these things. There's always some kind of physical cutoff involved. Okay, and so these are just different ways of doing the same thing. Anyway, that's a trivial little exercise, but it's fun if you haven't seen it before. Yes. Okay, thank you. Okay, so all right, so let's in our model example, then in our usual example, let's now see how we normally encounter the ultraviolet divergences. So we compute diagrams like this, for example, and here we get some actual mass squared that you get from the 2-point function, or some change to the 2-point function to here we get the sort of famous quadratic divergence here. And for this guy, the 4-point amplitude that I would compute, it has a piece. It has a quartic coupling piece plus this correction. So this looks like lambda naught, schematically minus lambda naught squared over 16 pi squared log some cutoff over p, or some cutoffs over p squared with some coefficient. Let me again uncharacteristically just once write down an actually correct formula. Okay, so this M4 is really lambda naught minus lambda naught squared over 32 pi squared, and then you go to Feynman parameter space, and you get an integral that looks like log cutoff squared over m naught squared. You're literally just doing the Feynman integral calculation, and then you get a similar thing from the T channel and from the U channel. Okay, so that's the answer you get. There's our famous logarithmic divergences and the power divergence here. Okay, the power divergence for the mass squared. Now, as I said, the real world has some actual cutoff, right? So whatever the actual theory of the world is will give some actual finite answer. And and here we've made a guess. We've made a guess for what's going on by regulating in some particular way. And again, the crucial thing is that the low energy physics is not going to depend on the details of the guess. Now, in order to illustrate this extremely simple point, but just taken out of the context of anything that seems mysterious and weird about field theory, let me talk about it in a much more trivial setting. And this setting is slightly too trivial because we're not going to have the analog of the logs in this example. But certainly psychologically, it has most of the important points in it. So instead of talking about this funny field theory, imagine I'm trying to model a piece of rope. Okay? Nice piece of rope. Now, what's actually going on to the piece of rope? The actual rope is made out of atoms and molecules and has some sort of complicated structure, right? And yet, if I want to look at what's going on to the rope from long distances, I wave the rope. I know I get some waves that go down the rope. So I have some actual atoms and molecules, some sort of complicated structure for the rope. There's some scale here, which is like the intermolecular distance scale or whatever. There's some scale a molecule. But at long distances, I just have a rope. And I know that all that matters in describing the waves on this rope are, does it matter what kind of material it was made of? Does it matter what the molecules are? What do you know? What are the things that matter for the propagation of waves on this rope? The tension and the mass per unit length. Those are the only things that matter. So we know that. It's the tension and the mass per unit length are what matter. Okay? Now, but let's say you had some idea about that, even someone told you that, but let's say you were too dumb to discover the wave equation. Okay? By the way, I mean, this is a general fact of life in theoretical physics, and I'm going to say this word many times. Dumb, when I use the word, is not a pejorative. Dumb is good. Okay? Clever and ingenious is bad. Dumb is good. And this is a deep fact about our field, right? When you're too clever and too ingenious, it's you as a human being who's entering the fray. You as a human being suck. Okay? What's really great is the universe and the structure of the laws out there. And you might go some distance because you're very clever and ingenious and smart, but trust me, you're nothing compared to the vast greatness of the laws that are out there. And at some point, your cleverness and your ingenuity will fail you. That's not the point of physics, to be clever and ingenious. The point of physics is to discover simple and deep laws and to exploit simple and deep laws. So simple and deep and dumb is good. Okay? So when I use the word dumb, it means something good over and over again. And you always learn something when you do the dumbest thing first, because 80% of the time it works. And 20% of the time it doesn't work, and you learn something very valuable, which is why the dumbest thing didn't work. So then you know what the second dumbest thing is. Okay? And typically you don't have to go too much further than the second or the third dumbest thing until something actually works. It's a way better way of living than constantly being scared that you have to do something clever and smart. And no, that's not the way. It's certainly not the way field theory is. Field theory is your friend. It's this massive, very powerful friend that never fucks up. It never screws around with you. Right? Just do the dumbest thing and it normally works. I promise you. Okay. Anyway. So here we're going to be dumb. We're not smart enough. We're not, it took fucking Laplace to come up with the wave equation, right? Or whoever it was. We're not Laplace, right? So what am I going to do? I'm not Laplace, but I have access to Mathematica. Okay, so how would you model this rope? I'm telling you, model this rope. You don't know about the atoms and the molecules. You kind of see it as some tension, some mass. How would you model it? Give me a model for the rope. Any model? Masses and springs, thank you. Okay? So, is the actual rope masses and springs? It is not. Okay, but who cares, right? I'm just making a model, right? So here's my model, and here's I have a bunch of masses and springs. I'm going to say the masses are m, the spring constant is k, and the separation is delta x, right? And you just take this bunch of balls and springs, you put it on the computer, you use dsolve, and poof, and tuck, 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 and you get these amazing, wonderful patterns. You don't know the wave equation, nothing, right? Now, what would you actually do, though? You see, this is your model. You don't know. You choose your delta x. You choose a delta x small enough so you haven't seen it in the rope yet. Okay, fine. Delta x is a nanometer. Very good. I haven't seen it. I choose delta x equals a nanometer. But you're going to have to figure out what the parameters of your model are, right, in order to actually match the actual rope that someone has handed you. So what you would find, and how would you do it? You see, you don't even know about the wave equation, right? But what you do is say, well, if I put this initial condition, this is what the wave pattern looks like. If I put that initial condition, this is what the wave looks like. And I just find how I have to tune my m and my k in order to match the actual rope. Now, we know what ends up being matched, right? What ends up being matched is the tension and the mass per unit length, right? So the tension is k delta x, and the mass per unit length is m over delta x. Okay? So from the actual observed rope, once you choose your delta x for your dumb model, that's not really what's going on, right? You're going to have to find some k and some m that matches t and mu. Now, let's say you now say, I'm going to take delta x to 0. I want to take the continuum limit of my model. Oh my goodness, m is going to infinity. Should I be scared that, sorry, m is going to 0, k is going to infinity. Should I be scared that these things are going to 0 infinity as I take delta x to 0? No, I should not be. This is a dumb model. This is not the real world. This is just my dumb model of balls and springs. However, importantly, let's say there's a second dumb person, and they choose a different delta x. Are we going to agree on the model? No. Right? Their model has a micrometer. My model has a nanometer for delta x. However, we'll also not agree on our m and our k. They'll have an m and a k. I'll have some m prime and k prime. Well, we'll have to choose them differently. But we're going to agree on the long-distance physics. Right? We're going to make the same waves so long as there are distances much larger than either one of our delta x's. And notice, of course, you can take the model too seriously. After all, if I make the wave, the size literally comparable to delta x, my dumb model matters a lot. Okay? And then the two different models will differ drastically. So the models are not going to be identical, but they will agree in a power series in the delta x squared divided by the wavelength squared of the long distance waves that we're talking about. All right? Is that clear? So this is just to make totally obvious that this is the analog of bare Lagrangian, right? You're making a model. You're making a sort of a choice for how to describe the physics. Anyone can make any choice they like, but the parameters have got to be taken from experiment, right? You have to sort of match some actual observable that you can see at very long distances. And once you do that, any two people who match those things are going to give you the same predictions up to power suppressed corrections. All right? And in fact, there is a formula, which in this case is so pretentious it's not worth calling it that. But anyway, you could call it the Wilsonian renormalization group equation, even in this case, that tells you how can I vary the parameters of my model with the cutoff to keep the physics fixed. Right? There's some formula that says that delta x dd delta x of m is equal to something in order to keep the physics fixed. Right? So delta x dd. Okay. So for example, delta x dd delta x of this is just k. Sorry. That's right. Right, so delta x dd delta x of k is just k. That just reflects the mass dimension of k, for example. Yes.
Like, I'm so dumb that I choose not many parameters to model this system.
Well, it would be, in this case, it would be the question was, can I be so dumb as to choose not enough parameters to model the system? In this case, it's hard to be so dumb because these parameters all have different units. Okay, you could, in more interesting cases, you could, for example, we could talk about examples in field theory later. You could put unjustified relations between the coefficients of different couplings in a Lagrangian. And this is the point about being dumb. There's nothing wrong with being dumb so long as you trust field theory. Field theory will tell you when you're being too dumb. And it'll tell you because you'll do a calculation and it'll say, actually those things are no longer equal even though you said they had to be. Okay? So you should never be frightened. It's even a good exercise to be dumber than you thought you had to be and then see if you could have been dumber. Okay? But in this case, we can't be so dumb. Yes.
4 minutes over. So
yes. Oh, okay, great. Yeah. So, all right. So in this case, we have these RG equations. We can call this the Wilsonian RG. Wilsonian RG is just a statement. How do you change the bare parameters of your model with the cutoff to keep the physics fixed? Okay. All right. So we saw this in our dumb toy example. And next time we're going to come back and see this in field theory. Okay? And let me just give you a little précis of this. So we'll first talk about it in the way that you've all seen in your courses, just at one loop. We'll go back to that field theory example that we worked out. And we'll just compute it one loop, and we'll see indeed, that it is possible once you express everything in terms of the physical quantities, you see that all the dependence on the cutoff goes away, blah, blah, blah. All those things that you've seen in field theory courses we'll review. But then there's also the fact that there's a very nice equation that tells you how to change, for example, the coupling lambda naught with the cutoff, capital lambda, to keep the physics fixed. So that's the non-trivial Wilsonian beta function for that coupling. But then you can ask why this miracle happened. At one loop, it kind of seems trivial. You do it, and that's it. But in fact, it's not trivial. It has a lot of teeth. If you just ask the question, what does it take if I just write out without doing the calculation? I imagined I did a calculation, 1 loop, 2 loop, 3 loop, 100 loop. I just write out the structure of the answer that I get, organized in powers of the coupling constant, and the logarithms that can make an appearance. Then this innocent sounding claim that it should be possible to change the coupling constant with scale, with the cutoff, to keep the physics fixed, actually makes an astonishing prediction that once you know the coefficient, once you do a 1 loop calculation, you know ahead of time, without doing a 2 loop, 3 loop, 100 loop calculation, the result of a certain 2 loop, 3 loop, 100 loop calculation. Okay? In fact, the leading logarithms that you get to all orders are totally fixed by the quantity that you see at 1 loop. And similarly at 2 loop, the subleading log that you show up at 2 loop determines the subleading log at all loop order after that. This is the teeth of the renormalization group. Okay? It makes an amazing prediction about the structure of Feynman graphs without having to do any calculations ahead of time. Right? So this very intuitive seeming statement actually has some teeth. We're going to then try to understand where that comes from. Okay? And to understand where that comes from, we have to invert the usual organization of thinking about quantum field theory instead of graph by graph, to go back to the Wilson's picture and think about it scale by scale. All right, thanks a lot.
Right, so unless anything changed that I wasn't told about, we have no fourth lecture today. That's correct, right? But there is coffee outside. So have your coffee, then have your soccer or other activity of choice. Talk to the speakers. We'll see you again tomorrow morning with Nima again. Thank you.
How to do
Yes.
because we just repeated all the stuff that Anish did for like the
Oh, yeah. Right.
but there's
Getting the actual log at 1 loop is a very nice thing that you might imagine doing. The thing that's very conceptually hard is how to see the exponentiation. How to see that the 2 loop, 3 loop, all loop logs are given by the 1 loop. Right. That's very hard. And I think that really needs some big conceptual ideas. I'll say a little bit about it tomorrow. So we don't have to think that way in the Wilsonian picture, precisely because the Wilsonian picture is so off-shell. It's deeply Euclidean, and it has all this off-shell stuff, these virtual fields, all this stuff. That seems like the best way of thinking about things. The only hope I see for understanding things on shell is related to this fact that Kahn and Primer and friends found this Hopf algebra structure that controls the old VPHD way of thinking about things.
which is doing the
Which
resummation.
is doing the resummation. Now, because we've seen that Hopf algebra structure, close analogs for it elsewhere in the on-shell world, there's a hope that maybe there's a conceptual understanding, but it have to be at that level. I don't think it's some sort of simple trick. This is something sort of deep, because we have to understand something that we normally see from a Euclidean perspective, from a Lorentzian perspective, in a way, unlike amplitudes, where the question is not a very local